Welcome to our global partners. Before we get started on today's VM Live, like always, I have the pleasure of starting with some kickstarts. So as a reminder, like all VM Lives, today's VM Live is being recorded and we're going to make it available for you for playback in about 24 to 48 hours after your session. We will post it in, if you go to Partner Connect, training, and then you'll see Partner University, but VM Lives are right next to Partner University on that tab. Click there and the playbacks are at the top right. But we don't want you to always watch the playbacks. We want you here live. We pride ourselves in finding the best subject matter experts inside VMware to deliver you live messages to help you learn, market, sell, and deliver our products and solutions. So because we have some great subject matter experts here live, we're asking you to use the Q&A. And don't use the Q&A just for questions. Post your questions, your comments, your thoughts. Be part of our conversation today by using that Q&A box. Lei, welcome to your VM Live. You got a whole crew here, so let's get started.
Thank you, Teresa, and thank you for VM Live inviting me, Bhushan, and Manish to give a webinar on modern app connectivity solutions. So it's a relatively new joint solutions that we just launched last month, and it's comprised of two products within VMware. So the first one is NSX Advanced Load Balancer, and it's also known as ALB Networks because we were acquired by VMware about 2 years ago, a modern multi-cloud application services platform. We also have Tanzu Service Mesh, which is developed by VMware. And we will go into details about each products, but most importantly is we want to talk about how they can help today's customers and partners to solve their app connectivity issues. Okay, so before we start, just a quick intro. My name is Lei Yan, and I'm leading product marketing for ALB. And we have Bhushan. Would you like to introduce yourself just real quickly?
Hey everyone, my name is Bhushan Pai. I'm a senior technical product manager with the AVI product in network and security business unit.
Yeah. Manish?
Hey guys, this is Manish. I'm a technologist in Tanzu Service Mesh team.
Yeah. Okay, so as you get familiar with our voice, this is a quick agenda for what you're gonna, expect today. So first, I'm gonna kick up with a little bit background on why this modern app connectivity solution come around, because we talk to a lot of partners and customers directly, and we see when they are modernizing their infrastructure as well as applications, they go into a set of challenges, and I'll go through that. And we do think that with AVI and the Tanzu Service Mesh together, we're able to bridge the gap that a lot of them are telling us that they want to bring their Kubernetes clusters from lab to production ready. And then I'll turn over to Bhushan and Manish to go over the technical details and use cases. And today you will also see a demo coming from Manish. Okay, so let's get it started. Now, I think all of you are very familiar with the old world where you have 3-tier applications, right? And kind of, secured by a perimeter firewall. And it's usually deployed in the data center, maybe accessed by users from the branch. So a fairly simple and straightforward model. Now, today's app is very different, right? You can see that it's being, evolved from a monolithic architecture to a microservices-based one. And it's not centralized anymore. It's distributed across different environments, but you might be running VMs, but you still have applications which are running on bare metal, for example, or attached to a database that you haven't touched in years, and you don't intend to change it, right? So that's basically what the application landscape looked like today. Correspondingly, the infrastructure has also evolved tremendously. So instead of just data centers, you have now moved your workloads to different clouds, multiple clouds. So, and you also the branch has evolved tremendously into an edge network as well. So what you're dealing with is a very hybrid multi-cloud world, that the challenge to deploy and manage these very different infrastructures in a consistent way, it has been a challenge. So connectivity has been a challenge to support the modern applications that you have. Next, because of this distributed nature of applications as well as infrastructure, you really the trust perimeter has really dissolved in the sense that you have to deploy a zero trust security model, have to check everywhere, but then the attack surface has also increased tremendously. So in this case, how can you protect your applications and infrastructure from attacks, different attack vectors and vulnerabilities? So number two challenge is how can you ensure while you have connectivity across your network and applications, how can you secure your applications, right? Last but not least, our world has really become more complex because you might need to deploy very different products for different functionalities. For example, you have a Kubernetes cluster and you need to deploy ingress controllers. You need to have L4 load balancing and WAF capabilities before it getting to ingress. And if you have multiple clusters deployed across, you have to have GSLB in order to have multi-cluster and multi-site connectivity. So all of that, right? If you count the number of products that you have in the environment, you can probably run out of your fingers. And that becomes a very big problem because management, maintenance, upgrades has become tremendous operational complexity on the team. So that's what we set out to solve this, environment where today you might have a set of disparate tools that you're deploying in your lab environment, and you're trying to test out some concepts, which is great. You want to make Kubernetes work, right? And then you have to stitch together these products yourself. However, ultimately for enterprises, they want to be able to provide a set of consolidated services to their applications team, to their businesses, right? So it's very important. How can you bring that more like a lab environment to a production ready clusters? And then most importantly, you do have applications which are not in containers today. It might be on bare metals and VMs. How can you bring those applications together over a very distributed, a very heterogeneous environment you have today? So we identify these gaps in terms of connectivity, security, observability over a multi-cloud deployments as a set of gap that we need to address. So that's why we bring these two products together, Avi, the NSX Advanced Load Balancer, and Tanzu Service Mesh to help you to bridge that gap. Now, without further ado, let me turn to Bhushan just to talk a little bit about the Avi architecture and what we do as ingress services.
All right. Thank you, Lei. Yep. Let's talk about the ingress services. Whenever you have an application deployed in a Kubernetes cluster, you need some way to expose that to the external world. And that's where the ingress services come in. These might be managed by multiple teams, like developers might be managing the applications deployment, security people, security team will manage the network policies, authentication, DDoS mitigation and detection kind of a role. And there can be operations team to which manages the networking and the observability, debugging the whole ecosystem basically. So these requires other features like traffic management, whether it be local or global, if you have a single or multiple clusters across data centers or sites. You need service discovery using integrated IPAM and DNS so that whenever new service comes up, it's automatically ready to use. And there needs to be a way to manage all the certificates that which are used in the authentication process. And to bring this all together, there needs to be an end-to-end observability platform where you can easily see if something is going wrong, at what point in the traffic path is it going wrong, and how to easily correct it. So that's where Avi comes in. Avi gives a single consolidated solution to all of these problems. It's a single solution which provides everything right from ingress and load balancer, which is the default thing to do for an ingress service. In addition to that, it provides web application firewall, integrated IPAM and DNS to manage the IP addresses and the FQDNs of your service, and also GSLB, and all of this under a single license. This gives operational simplicity so that your teams do not have to manage the desperate solutions one at a time. And this brings together the dashboards of all of these features into one product, so that you have end-to-end observability to debug your applications. And all of this can be managed in a cloud native way directly from your Kubernetes configurations. So everything that all the Ingress services that Avi provides can be configured directly using Kubernetes manifest or some CRDs to customize the configuration. Let's go to the next. Yep. So before we move into the how this works in the Kubernetes world, just a quick overview of what the Avi architecture looks like. So unlike any other load balancer in the market, Avi has a very modern distributed architecture. What that means is there is a centralized control plane called Avi controller, which manages multiple data plane entities called service engines. Now, all of these are completely software. So, Lei, can you please? Yeah. So this can be deployed for any kind of workload, be it a bare metal x86 servers, virtualized VM or containers, both on-prem and public cloud. Since this, with the centralized orchestrated and the software being complete, so the product being completely a software product, it can scale really easily. Can you click one more, please? Yeah. So since this is a completely software product, the service engines can scale elastically while being managed centrally from a single Avi controller. This gives you a elastic, resilient fabric where even if a service engine dies, the controller is intelligent enough to spin up a new one. And as the traffic flows through these service engines, it gathers hundreds of different analytics and metrics, which gets bubbled up to the controller, where it shows you in a rich observable dashboard of what's happening with your applications. Along with that, it also uses these metrics internally to automate the scale out of these service engines, so that you get the elastic fabric. Along with that, we also have a service called Avi Pulse, which lets you keep updated with the latest mod security rules for web application firewalls, help you troubleshoot and debug your infrastructure itself, as well as for GSLB purposes. It also keeps your global database, GSLB database updated, and various other functions with that. All right, with that, let me hand it over to Manish to take you over the Tanzu service mesh portion of this.
Yeah, and in the meantime, Teresa, do you see any questions coming in while Manish brings us his screen? Any questions we can address right now?
No,
Partners?
I don't see any questions right now, but this is a great time to remind partners that if they do have questions, we are taking those in the Q&A. Thank you.
Okay, thanks, Lei and Bhushan. Can everybody see the slide here?
Yep.
Perfect. Okay. Hey, so as Lei talked about how the landscape has changed in terms of evolution of application as well as infrastructure, and as Bhushan said, how Ingress is becoming a very critical functionality in exposing your services from within your clusters, right, or multiple clouds, and the kind of services that sit around Ingress, and how Avi kind of consolidates most of those services into one product, like GSLB and WAF and Ingress controllers and L4LBs, which kind of simplifies the whole operation of the Ingress, right? So let's now go and try to understand Tanzu Service Mesh, which is the second product which builds this solution. And so what we're going to do is we're going to do a very high-level introduction of the architecture of Tanzu Service Mesh. We're going to then talk about the use cases of the solution, and that's where I want to spend most of the time today, in terms of trying to explain how these products together enable and deliver certain critical use cases for the customers, right? And the reason for actually building the solution, right? So let's start with the architecture of Tanzu Service Mesh. As you see here, there are two clusters here, and there is a global controller on top. So global controller is what is the main control plane for Tanzu Service Mesh. This lives in a SaaS environment right now with a roadmap feature of moving it to on-prem by the end of this year, beginning next year, right? But right now it does live in SaaS. And this controls deployment and management of Tanzu Service Mesh on audio clusters. The way to deploy and onboard the clusters onto Tanzu Service Mesh is pretty straightforward, and we'll see that in the demo. So I'm not really going to get deep into that. But you can very simply onboard your Kubernetes clusters, and these Kubernetes clusters, by the way, could be any Kubernetes cluster, right? We support all the, of course, all the Tanzu Kubernetes clusters like TKGIs, M's, and S. We support any other non-Tanzu clusters or native Kubernetes clusters, also including managed Kubernetes clusters like GKE, EKS, AKS, and so on and so forth, right? So it could be any Kubernetes clusters which is supported by Tanzu Service Mesh. And once they are onboarded onto the cluster, what Global Controller does is it gives you a couple of YAMLs which you deploy on your cluster, which downloads all the bits and bytes of Tanzu Service Mesh on each of these clusters. And that portion of the Tanzu Service Mesh, which is local to the cluster, has its own controller again. And it also has sidecars, which are load balancers, which sit next to your application in a pod. So as soon as you deploy any pod in the cluster, which is enabled by Tanzu Service Mesh, that pod will also have another container automatically getting injected to it, which is a proxy that we control from the local controller. Now, all the traffic that goes between the services within the cluster and even across the clusters, right? And that's, we're going to get into that, how we solve the across the cluster issue, always goes through these sidecars. And that is what is a mesh, right? So every request, every response, all of the traffic will go through the sidecar. When it enters the other service, it actually enters through the sidecar, right? So these sidecars now create a mesh, and that's why it's normally called a service mesh, right? And the fact that we have these sidecars now injected in all the containers, application containers, gives us a lot of power to do a lot of things, right? You can now look at all the traffic. You can manage all the traffic. You can, when I say manage, you can actually, based on the policies, do things to the traffic depending on the health of the endpoint, depending on your deployment pattern, and so on and so forth, right? So it kind of opens up a lot of use cases for the users once you have so much control in terms of controlling the traffic from a service and controlling the traffic which enters the service. Yeah. So the good thing about this architecture is Global Controller allows you to configure policies. Local Controller takes care of the local policies. So even if the Global Controller goes down, the traffic does not get impacted. It does not sit on the data path. It just configures the data path, but does not sit in line. So anytime, even if you lose the connectivity to Global Controller, it doesn't really affect anything. Yeah. Now, taking a step further, what we have is a concept of global namespace, and you would have seen that in the previous slide also. And this is a very, very unique construct, and I would like to spend a couple of minutes on this. So this construct actually enables the complex use cases in this complex world that Lee talked about, right? Which is a multi-cloud, multi-cluster hybrid world, right? Where our applications are deployed. What this construct does is it enables you to kind of stretch the boundary of the service mesh across your clusters and clouds, and also scope it, right? So it makes a boundary for an application where you now deploy your application without having the need to understand where those applications are residing. So it creates an abstraction boundary, right? So once you have applications within a global namespace, it doesn't really matter where they are or in which form and shape they are. What GNS does is it automatically plumps the networking, DNS, so on and so forth, certs and so on, right? To be able to give you connectivity and secure connectivity across clusters and clouds. So for example, in this case, let's assume there are two clusters, as we see, and there are these two namespaces with services running on them. And let's assume GNS comprises of both these clusters and both these namespaces. So what's going to happen is, as soon as you create a GNS, and we'll see it very clearly in the demo, by the way, but as soon as you create a DNS, service 1, for example, will automatically be able to talk to service 5 using a certain domain name, which is given by us through a strong identity CA mechanism. But it can just talk to service 5, right, without the user doing anything. And that's because GNS automatically plumbs the networking in DNS. So it could reach service 8 just by calling service 5 dot the gnsname.com, domain name.com. Yeah, so that's how easy and intuitive it makes it, right? So if you break into the functionalities that GNS provides, and this is a very unique construct which nobody has in the industry, right? Right now. What it provides now is, of course, the fact that you can discover your services across clusters and clouds automatically. It gives you an identity to the services. Now, this is important. The fact that we are able to provide identity to all your services across these clusters and clouds helps us. And by the way, these are very strong identities based on a lot of internal factors like service accounts, where your deployment is done, the namespace, the service name, and so on and so forth, right? But once we are able to provide the identity, the connectivity that happens between two services now within or across the clusters can be secured. And that is what enables use cases like MTLS between services, a secure connectivity between services using service mesh, right? The third is policy. Now, this becomes also a boundary where you can start applying policies. Like I just mentioned, right? You can apply a policy, hey, all the services within the GNS need to be MTLS, right? Encrypted. So that is one policy in itself. You could have various other policies, right? Hey, if within this GNS, I do not want to expose any service to outside the world, or I don't want any connectivity to go outside the world, right? And pretty complex policies also, like, for example, I do not want a user sitting in a country foo to be able to access a service A within this GNS if that service is talking to a data or accessing a data which is, for example, a secure data like PII data and so on and so forth, right? So I can have those kind of policies. I can have really, really complex policies too, apart from, of course, simple policies that we just talked about, right? The last but not the least, and you will see that in the demo, is observability. The fact that we are now able to connect these services across clusters and clouds, we're also able to show a very intuitive graph and a real-time graph of this connectivity. So we call it a service graph. It's very cool stuff, and you'll see that in the demo. What it shows you is how all of these services are talking to each other. And not only that, by the way, it also shows the golden metrics of what is going on between these services in terms of latency, error rates, so on and so forth, right? So that's a very, very important tool for the users to figure out what's going on with the services, yeah? And by the way, we're able to collect that data for the simple reason that we have the sidecar running next to the application container. So we are able to collect all the metrics, rich set of metrics that you normally cannot, right? If you don't have control on the traffic, right? Also coming to this slide now, specifically, as we talked about GNS being isolation boundary too, right? So nobody from outside the GNS can talk to any service within the GNS and vice versa. The only way you can actually start exposing a service from outside, within the GNS to outside world, is by creating something, a feature which is called public services, right? So only when you create a public service can you expose a service outside the GNS. Now, once you expose the public service, right, it is pretty much like an ingress functionality in the Kubernetes cluster. When you expose the ingress, you are also looking at different services around that ingress, right? And this is what Bhushan talked about, right? You just don't want to expose the service. You also want to give it a name, an FQDN, which users can access using, right, that name. You also want to maybe set some policies on that public service. For example, I want this public service to be highly available across the clusters, right? Which means that, hey, if I deploy the same service in some other cluster, just magically make it highly available, right? You may want to do that, and if we can do that, that's going to be awesome, right? You may also want to define policies like global service load balancing. Hey, if my application or the service is running on 2 different sites, can you enable global load balancing for me automatically? So when users are accessing the service using the FQDN, they are routed based on the GSLB algorithm to the healthiest site or to the site that's closer to them, and so on and so forth, right? So you do require all these services, which kind of make the use cases pretty intuitive for the customers and the users. And that is where this integration is important, right? Not only does it provide you all the functionalities of a service mesh from an east-west service-to-service communication perspective, it also provides you feature set when you're trying to expose a service outside the mesh, which are all the ingress feature sets we talked about, which RV has, right? So having TSM and RV work together in an integrated manner enables those use cases automatically for you, right? And we'll get into those use cases very, very shortly. And the fact that both of these have a very similar architecture, and they run on and support any infrastructure, underlying infrastructure, not only Tanzu ones, but also the ones which are not Tanzu, right? Enables customers to actually run it anywhere, right? Okay, let's go to the, yeah, so we did talk quickly about these benefits which the solution provides. You of course get a multi-cloud experience. You're able to not only manage your applications deployed on a single cluster, but across clusters and clouds. And this is a complex world we talked about, right? And when we're talking about management, we're talking about providing connectivity automatically, providing security automatically, securing the communication between services, observing the services, right? And so on and so forth. So you get that multi-cloud experience out of the box. Also the fact now you have a unified policy. We talked about how you can now, GNS becomes that boundary where you can now start applying policies to all the applications within the GNS, right? And the fact that we're integrated with NSX Advanced Load Balancer, which is RV, make sure that using the same framework of GNS, you can start applying policies of advanced load balancer, right? Like GSLB and L4 load balancing and WAF and so on and so forth, right? But through a single pane of glass of GNS. This, of course, brings you in the operational simplicity, right? You don't have to go to different point products, operation sites and UIs and so on and so forth. You have a single UI, you have a single abstraction using which you configure, manage, and control your application, yeah, which is a great benefit day two. Yeah. Okay, this is an important slide which kind of talks about the use cases which this solution enables. We talked about seamless app connectivity, very important use case in a multi-cloud world where your applications are distributed across different clouds and clusters. This enables you to automatically discover and connect the services. Demo is going to make it very, very clear. So I really want to get into that demo sooner. It's going to make it clear how intuitive it is to do this. It's not a question of configuring a lot of things before you get this use case delivered, right? It is very intuitive and just a few clicks. App continuity and scaling is another important use case that this enables, which is the fact that you can now enable high availability policies, GSLB policies on your applications, which enables you to have a business continuity in terms of even if the cluster goes down, your application is still up and running and so on and so forth, right? And also scaling. If you have a lot of traffic that is, there's a spike in traffic, for example, for your service, or we have a capability of auto-scaling your application and guaranteeing a certain SLO, which is determined by the service level indicators that you can actually configure for your application, right? It also lays foundation for the zero trust security, right? You can now not only have end-to-end security between your applications within the service mesh across clusters, but also from the north-south perspective utilizing NSX Advanced Load Balancer. And last but not the least, we talked about the fact that it simplifies the operations, right? So the whole DevSecOps model gets very, very simple, where you have very clear-cut roles defined and what they can do as a part of this product. And each of those roles can now deliver the use cases they're supposed to in a very, very, very simple and intuitive manner. Okay, without much ado, let's get into a demo. Before we get into this demo, let's have a look at the demo setup. For this demo, we have 3 Kubernetes clusters across 2 different sites or regions, all of them onboarded onto TSM. We also have RV NSX ALB, which is configured on both the sites to provide infrastructure load balancing as well as GSLB, with the on-prem site acting as the GSLB leader. In this demo, we'll showcase how TSM's global namespace construct helps us deploy an application across multiple clusters seamlessly, and how it automatically enables both connectivity and security for the application services across these different clusters and clouds. We will showcase how to create an application SLO and how increasing the traffic to the application has an effect on that. We will also demonstrate how TSM's autoscaling feature automatically scales up the desired application instances to meet the SLO guarantee. But as the traffic keeps on increasing and the on-prem cluster resources get exhausted, we will showcase how post-deploying the same application onto the cloud cluster, which can also be triggered automatically, TSM configures RV's GSLB to steer the part of the traffic to the other cluster, which is a typical cloud bursting use case. At this stage, we'll bring down the front-end service on the cloud to see how the traffic is now steered back to the on-prem cluster, and how TSM's global namespace helps make this transition more seamless than what can be achieved by just a pure GSLB. So without further ado, let's jump into the demo. Let's start by looking at the TSM dashboard. Here we are looking at the cluster overview page. As we can see, we have 3 clusters already onboarded across 2 different sites. 2 are on-prem and 1 on the cloud. To start with, we have already deployed our Acme application, but with a little bit of twist. The deployment has been split across 2 on-prem clusters. As we can see, most of the services are running on on-prem 1 cluster, including an internal load generator. But some services of the application, like Catalog and its DB backend, are deployed on on-prem 2 cluster. On the 3rd cluster, EKS Cloud, there is nothing deployed. It's a brand new cluster that was very recently onboarded. By the way, onboarding a Kubernetes cluster on TSM is very simple. All we need to do is click onboard a new cluster, give it a cluster name, for example, test, click on generate security token, and then apply a couple of onboarding YAMLs to the cluster. What this does is deploys TSM operator on the cluster, which then calls back home to TSM SaaS and establishes connectivity on which all the bits and bytes of TSM are pushed onto the cluster and deployed. Once that is done, you can see your cluster on this page. At this stage, under the cluster view, you can look at which services are talking to each other within the cluster by looking at the real-time service graph that TSM provides. You can get more details about your service-to-service metrics, like performance indicators at each hop, latency, error rates, extra, and also specific service level golden metrics by hovering over the service. We can also click a specific service, for example, shopping, which shows us a spider graph view of all the services shopping is connected to. This view also shows all the node level heat map of the nodes where the services have been deployed. This helps in correlating any issues in the service with any underlying infrastructure problems. The performance tab gives us more detailed information about how the service is behaving, including how it's doing with respect to its SLO or how it's reacting to autoscale triggers and so on and so forth. We'll get into details of each of that, but before that, let's look at other configurations that we have done for this demo. As I said, we have RV ALB configured to provide GSLB across 2 sites. But we can also use Route 53. On the TSM side, all we need to do is under integrations, create an account pointing to the RV GSLB leader. For Route 53, you can add Route 53 account. To add an account is as simple as providing the credentials and access details of RV control. At this point, let's look at our RV setup as we log into the RV controller. And by the way, this is the leader controller we can see. We have RV providing GSLB across 2 sites. Let's have a look at that. One is on-prem and the other is on the cloud. And this is where our clusters are residing. We can also see that we have delegated a couple of subdomains to GSLB, TanzuServiceMesh.net and tanzuservicemesh.com. We have also defined SLO for an application. For this demo, we have defined an SLO called frontend to represent the shopping service of Acme Fitness application. We have set up the service level indicator of P99 latency to be less than 300 milliseconds, and we want these conditions to be satisfied 90% of the time, based on which we calculate the monthly, weekly, and daily error budget. At this stage, we can apply this SLO to the front-end service. We can also assign it to a group of services defined by TSM's service group. But in this case, we are applying it to a specific service, which is shopping. A quick review of what we configured. This gives us a summary of the SLI and SLO definitions that we configured. The only way to expose a service outside TSM is by creating a GNS and exposing it as public service. Since we haven't done that till now, let's just access the front-end service port by forwarding the shopping pod using kubectl. Let's look at all the services running on-prem 1 cluster. And we can see shopping is running there. Let's expose it using port forward of kubectl on port 3000. Let's try and access this application. We can see that we can access our application and it seems to be working fine. But it's not showing any items in the catalog. And that's because our catalog service is running on a different cluster to which we do not have connectivity. At this stage, let's create a global namespace. Let's call it Acme and give it a domain name called acme.com, which provides identity and connectivity to the service within the GNS, irrespective of where they're running. The next step is important. This is where you define what comprises of your global namespace. It's a rule-based configuration where you can attach a cluster and its namespaces to the GNS. Let's add the cluster on-prem 1 and its namespace Acme. At this stage, you can also see the existing services deployed in that namespace. And you can see all the services there except catalog. Let's go ahead and add the other cluster, which is on-prem 2, and its namespace Acme. Here you can see the catalog service. Let's go ahead and also add EKS Cloud Cluster. As I said, it's rule-based, so the services may or may not exist. And as and when the services are deployed in this cluster's namespace, they will become a part of the GNS. Let's configure the public service now. Here we can pick up the front-end service, which is shopping, and give it a public URL. Let's give it a name Acme. As you can see, my subdomains that I had delegated to Avi, tanzuservicemesh.com and tanzuservicemesh.net, they got already populated here. Let's pick up .net, and now let's add a default health check for the service. Let's look at the summary, and everything looks fine. The application can be accessed at acme.tanzuservicemesh.net. As soon as we finish creating the GNS and go to Avi, we can see the TSM automatically created a GSMB service in Avi with the endpoint to the cluster's ingress gateway. Now, if we access our application using the public URL, we can see that we can now access the complete application, including the catalog. So you can see all the catalog items here, right? And all this just worked automatically by creating a GNS and making these clusters a part of the same GNS. If we now go to a different view, which is a GNS view on the TSM dashboard, you can see how services within the GNS is connected to each other across the clusters through the GNS service graph. Another important point to note is that all the connectivity between the services within the cluster and across the cluster is encrypted by default using MTLS. If we now look at the performance tab of the service, we can see that service is behaving great. There are no SLO violations. It's all green and looking good. Clicking the details for the SLO verifies that there is no error budget burn and P99 latency has not exceeded the threshold of 300 milliseconds that we configured. The instance count is also stable and not increasing. And all of the metrics like requests per seconds, P50 latency, and so on are all fine. At this stage, let's send some additional traffic to the application's public URL, which is tanzuservicemesh.acme.net. Now let's go back to the performance view of the service and check if this traffic has any effect on the service level indicators and hence the SLO of the service. We can already see how it's affecting the request per second. P99 latency seems to be increasing, and it seems to have crossed the threshold. We can also see that SLO has turned from green to yellow, which is a warning. And looking at the details, it shows how the error budget is depleted. If we don't react to this traffic, we'll soon violate our SLO as our error budget gets completely depleted. And sure it does. And we can see that we don't have any error budget left. And the color changes from orange to red, which means that we are in the violation of the SLO. What we would have wanted though is for the system to react to this increase in SLI. And based on that, do certain actions like auto scale the services, which are the bottlenecks, which helps us guaranteeing the SLO. But since we do not have instance auto scaling enabled, we see that the instance count is remaining the same. This brings us to the PRTC feature of TSM, which is an advanced auto scaling feature of TSM. For this demo, we already have it configured, but I just did not have it enabled. As you can see, it seems to have already figured out that the desired value of the number of instances should be more than what it is currently. So let's enable it for all the services. And once it's enabled, we'll look at the ASD configurations for one of our services. Let's look at the ASD configuration for our shopping service to understand the configuration better. As a part of this configuration, we have defined the mode to be efficiency. Efficiency mode means that you can scale out or scale in when needed. There's another mode called performance, which is always scale out. We have defined the min and max instances, in this case 1 and 10, and the metric based on which the definition is applied. In this case, scale up if P99 latency is greater than 300 milliseconds, and scale down if it's less than 50. Apart from P99 latency, TSM's autoscaler can also act based on other indicators like requests per seconds or request count or CPU usage millicores or percentage or memory usage bytes or percentage and so on. And you can see some of our other services using these. If we go back to our performance view now, we can see how we have started scaling up these services. There we go. And the effect it has on the key metrics, including P99 latency, on which the SLO is based. And as the latency continues to be under the threshold, our SLO has turned to green, which is healthy. In the real situation, we would have wanted this configuration enabled beforehand, and this would have helped us guarantee an SLO without violating it. This approach works, but if the traffic keeps on increasing, which is what we are doing in our case, our cluster will soon reach the resource limit beyond which you can't even scale anymore. At this point, what you would want is to trigger an application deployment to an empty cluster that we have on cloud and automatically steer traffic to that cluster. This is a typical cloud bursting use case. As that could take some time, we could trigger the same manually by deploying the application on cloud. In this case, let's go ahead and deploy the complete application to a single cloud cluster. Let's switch our context to the cloud cluster and deploy the complete application. As soon as the application services are up and running, and since the cluster is already a part of our Acme global namespace, TSM will automatically detect that the front-end application shopping has come up in this cluster and configure our RV GSLB to steer traffic into this cluster based on the GSLB algorithm, which by default is round robin. Looking at the RV configuration, we can see that we have added another endpoint to our Acme application, pointing to the new cluster's ingress gateway. Again, based on our configuration, this will take some time before the endpoint is flagged healthy. Using a utility which digs and curls the endpoint, we can see how we are accessing the service in a round robin fashion. Here we see it going into two different sites. In the next version, while configuring public services, users will have the option to pick up the GSLB algorithms like active passive, weighted round robin, or geolocation. At this stage, we have the application running in DR fashion, and we can now bring down the whole site, the cluster, or the service instance, and we should be able to still access the application. Let's try one of these scenarios and scale our front end in cloud to 0. Before that, let's look at our GNS view of the application, and now we can see 3 clusters and how the services are connected to each other across all the 3 clusters, thus providing high availability not only across the clusters from the north-south point of view, but also from the east-west point of view. Now let's go ahead and scale the shopping application on the cloud cluster to 0. As soon as we do that, please look at the window below. You can see we just got 1503, but apart from that, we are still able to access our application, even though my dig is still pointing to 2 different clusters. The reason the request is still going to 2 different clusters in a round robin fashion is because the outer GSLB will take some time to detect that the endpoint is not healthy, which is a few tens of seconds. Until then, the request will go to both the clusters. But as we saw, we were still able to access the application. And this happened because as the request came to the cloud cluster, the cloud gateway figured out that the local shopping application is not there anymore because we scaled it to 0. But since all the clusters are a part of the GNS, it was able to route it to the on-prem clusters shopping. Even for that amount of time, the power of GNS makes sure that the traffic gets routed to the cluster where the service is still running. This, of course, will work only in case when the service is down, but ingress gateway is not down, right? If the cluster is down or the ingress gateway is down, the GSLB trigger will come into picture, and as and when GSLB failure will happen, the traffic will get routed only to the cluster where the service resides. And now, as you can see, it's only going to a single cluster, which is on-prem. If we go into the GNS view, we can see that there was that small amount of time during which the request from the cloud actually went to the shopping on the on-prem cluster until the actual GSLB, which is RV, failed it over to only the on-prem cluster. Yeah, but before we get into this demo, so let's have a look at. Yeah, so with that, we come to the end of the demo. I hope you found it useful in terms of understanding how the solution combined together enables use cases that we talked about, right? Regarding connectivity, security, observability, and also complex use cases like cloud bursting and so on and so forth, right? What I want to now for the next minute also talk about is the future roadmap that we have with respect to the solution, right? What we saw today was a very, very important use case around connectivity, scalability, and so on, right? Where Tanzu Service Mesh with NSX Advanced Load Balancer was able to configure the GSLB capabilities of Advanced Load Balancer to provide certain use cases. In the next phase of the solution, we are also looking at not just configuring the GSLB, but also be able to configure regional load balancing capabilities of RV. In which case, now rather than having the endpoints go to each of the clusters they can now go to each of the original load balancer, thus creating a hierarchical model. This kind of gives you a lot of power at a single region on how you want to start routing your request within that region or within the clusters within that region. Yeah. So that is a very important use case that we are planning to do as a part of supporting L4 as a feature at the original site, right? We're also planning to support L7 at RV, where rather than uh, TLS getting terminated on the ingress gateways within the clusters of Tanzu Service Mesh, it gets terminated at RV. Hence, we will be able to now start applying policies like web application firewall onto your public services, right? So you can now create a public service and say, hey, you know what? I just don't want it to be highly available in GSLB, but I also want to enable WAF on this public service, right? Which again makes it operationally very simple and goes towards that zero trust access, which we talked about, right? So these are a couple of use cases that are coming up in the next phases. Another one, last but not the least, very important use case is Lei talked about application evolution, right? But we also did talk about challenges where not all the applications have been containerized or have been modernized and running in container infrastructure on cloud or on-prem. There is a lot of infrastructure and applications which mainly stateful, right, like databases and so on and so forth, right, which are still running in VMs. And when we talk to our customers, these applications are the bottleneck for their application or cloud modernization journey. And our customers are always saying that, hey, we would like to modernize as fast as possible, but you know what, we have some part of the application still residing in VMs, and it's going to take us some time to modernize that, right? But with service bridging, what we are achieving, and it's coming out very soon in next quarter, we will utilize NSX advanced load balancing service discovery functionality on the virtual machine infrastructures to be able to not only discover those virtual machines, but also able to sync that catalog into Tanzu Service Mesh utilizing one of our open source protocols called Hamlet. Now, once that happens, what you can now do is within the GSLB, like we just had connectivity within services, which were containers, you could just now start applying VMs. And you can access VMs just like any other service which was running on the container orchestrator like we just saw, right? Now, this enables two use cases. One, of course, that you can actually bridge to the VM. The second is the modernization becomes seamless. Now, as soon as when you modernize your VMs to the containers, you just move it to a container infrastructure or to a cloud, and as they are a part of the same GNS, nothing changes, right? The traffic can be managed to be routed to the newer instance. You can create policies on how much traffic do you want to steer towards a new instance and so on and so forth. And you can bring down the VMs when everything is fine. So it just seamlessly enables that use case. Yeah. With that, we come to the end of the presentation. Thanks everybody for joining, and we're open to questions and answers now.
Great, thank you so much. I'm surprised I don't see any questions. This was a lot of great information coming from the chat. You're very welcome for the demo. I like demos too. They're very insightful as well for me. So thanks for that feedback. I want to invite our partners. VM Lives are partner only VM Lives. So you don't have to be a subject matter expert. You don't have to sell that solution. This is our engagement hour with you, where you get free information to learn, market, and sell our products and solutions. And our 9:30 VM Live, we're going to talk about introducing VMware Cloud Web Security. This is a VMware SASE service available with SD-WAN release 4.4. We're going to cover some details on CWS. We're going to go over some use cases, some PNP, along with another great demo. So if you could join us for that session, that would be great. And like I said, the beauty of VM Lives for our partners is you don't have to be a subject matter expert. It doesn't have to be a solution you sell. This is our time with you. I promised you great subject matter experts for today's VM Live, and I don't think I disappointed. I want to thank the VMware team so much for their time today and delivering a great presentation and lots of knowledge. I know we didn't get any questions right now, and I know sometimes we leave these and we do think of questions. So if you have questions, you can always email me at vmlive@vmware.com. You have to include the session title so I can put you in touch with the right contact people. I want to thank you guys from VMware. Thank you so much for today's presentation, but most importantly, thank you to our partners. Whether you started your day or you've ended your day, be safe and have a great rest of your day. Bye for now.